Okay, good morning. So today we're going to, as I mentioned last week, we've started the part of the course where we're doing more things having to do with design, okay, than purely analysis. Today we're actually going to do analysis, but it's a type of analysis that leads to really interesting design issues. And we're going to follow it up on Wednesday with an application of the methods we're going to learn today to a really interesting and practical problem. So we're talking today about amortized analysis. And I want to motivate this topic by asking the question, how large should a hash table be? So how large should a hash table be? Anybody have any suggestions? Got to make a hash table. How big should I make it? Let's say it's a simple hash table, resolving collisions with chaining. How big should it be? Twice as big as you need. Okay, how big would that be? So twice the number of elements, for example. Okay? As I increase the size of the hash table, what happens to the search time? What happens to search time as I increase the size of the hash table? Yeah, but what does it in general do? It decreases, right? Okay? The bigger I make it, in fact, if I make it sufficiently large, then I essentially get a direct access table and everything's worst case order one time. So in some sense, we'll get back to your answer in a minute, okay? We should make it as large as possible. Okay, so that the searching is cheap. Flip side of that is what? Takes a lot of space, so I should make it as small as possible. So as not to waste space. Okay, so I want it big. Okay, and the happy medium, as we've discussed in our analysis, is to make it order n size for n items. Okay, because making it larger than order n, the payoff in search time is not payoff in search time is not worth the extra amount of space that you're paying. Okay, or at least you can view it that way. Okay. However, this begs the question, which is, how do I make it? If I start out with a hash table and I don't know how many elements are going to be hashed into it. Okay, how big should I make it? Okay, so what if we don't know? In advance. Okay, what if we don't know n? Okay. So the solution to this problem turns out is fairly elegant. It's a strategy called dynamic tables. Okay. And the idea is that whenever the table gets too many elements in it, gets too full, Okay, so the idea is okay, and we say, and that says the table overflows. Okay, we grow it. Make a bigger table. So for hashing, although there's going to be no point at which you could say that it overflows in the sense that it wouldn't be functional, at least if it was done with chaining. There would be, by the way, if you were doing it with open addressing. Let's say with chaining, there's when it gets too big, say, as many elements as the size of the table, what we do is we grow the table. So the way we do that is we allocate using, in a language like C, it's called malloc, or in a language like Java, called new, a larger table. So we create a larger table. We move the items from the old table to the new, and then we free the old table. So let's do an example. So let's say I have over here a table of size 1. Okay, and it's empty to begin with, and I do an insert. So what I do is I stick it in the table. It fits. Okay, so here I'm not going to do it with hashing. I'm just going to do it as if I just had a table that I was filling up with elements to abstract the problem. But it would work with hashing. It would work with any kind of fixed-sized data structure. I insert again. Oops, doesn't fit. Get an overflow. Okay, so what I do is I create a new, actually I'm going to need a little bit more space than that. I create a new table of size 2, doubling the size. And I copy the old value into the new. I free this one, and now I can insert item 2. So I do it again, get another overflow. So now I make a table of size 4. I copy these guys in, and then I insert my number 3. And we do insert here. We'll do 5. I guess I should be using ditto marks. That'd be a lot smarter. Okay, whoops. What am I doing? I overflow. So now I make one of size 8. Okay, copy these over. And now I can insert 5. And I can do 6. 7, etc. Okay? So everybody understand the basic idea. So whenever I overflow, I'm going to create a table of twice the size. Okay? So let's do a quick analysis of this. So we have a sequence of n insertion operations. Okay. What is the worst case cost of one insert operation? What's the worst case for any one of these? Yeah, it's order n. Okay? Order n. Whatever the overhead is of copying. If we counted it as 1, it'd be basically n, or n plus 1, because we've got to copy all those and then, okay? So it's order n, okay? So therefore, if I have n of those, so the worst case cost of n inserts is equal to n times order n, which is order n squared. Any questions? Does that make sense? Raise hands.
You're not going to have good n inserts. Not all of them can be worst case.
Yeah, not all of them can be worst case. Good. Okay? And in fact, this is totally wrong analysis. Just because one can be worst case order n doesn't mean n are necessarily order n. Okay, so this is totally wrong analysis. N inserts, in fact, take order n time in the worst case. Okay, doesn't take order n squared. So the analysis is correct up to the point where we said the worst case of one insert was order n. This, therefore, that's the wrong step. Okay, whenever you see bugs in proofs, you want to know which step is the one that failed so that you can make sure that you don't have a confusion there. So let's do the proper analysis. Okay, so let's let C sub I be the cost of the ith insert. Okay, so that's equal to I if I minus 1 is an exact power of 2, and it's 1 otherwise. Okay, so as I was going through here, it was only when I inserted something where the previous one had been the exact power of 2, because that was my table size, that's when I got the overflow and had to do all that copying. And otherwise, the cost, for example, for inserting 6 was just 1. I just inserted it. Okay? So everybody see that? So let's actually make a little table here so we can see this a little bit more clearly. Okay, so we're going to have I, and then the size of the table at step I, and the cost at step I. Okay, so let's see, the size of I, let's see, at step 1 it was 1, at step 2 it was 2, and at step 3, that's when, to get 3 in the table, the size we had to double the size here, so this is 4, and then 4 it fit, and then 5 it had to bump up to 8, and then 6 it was 8, 7 it was 8, 8 it was 8, and 9 it bumps up to 16, 16, etc. Okay, so that's the size. And let's take a look at what the cost was. So the cost here was 1, okay, to insert 1. The cost here was I had to copy 1 and then insert 1, so the cost was 2. Here I had to copy 2 and insert 1, so the cost was 3. Here I had to just insert 1, so the cost was 1. Here I had to copy 4 and insert 1, so the cost was 5. Excuse me? I think it is.
With I minus 1?
Yeah, see? It's I. The cost for 5 is I. Okay? Is for 5 if this is a power of 2. Okay? 1, 1, 1, and now we pay 9, and then 1 again. So that's the cost we're paying. A little bit easier to see what the costs are if I break them down. Okay, so let's just redraw this as 2 values, because there's always the cost for inserting the one thing that I want to insert. And now the residual amount that I have to pay is I have to pay 1 here, I've got to pay 2 additional, 4 additional, 8 additional. That makes the pattern a little bit easier to see. Okay, this is the cost of copying versus the cost of just doing the actual insert. Okay? Now, if you're taking notes, leave some space here because I'm going to come back to this table later. Okay? So leave a little bit of space because we're going to come back and add some more things in there at a later time. Okay? So I can then just add up the cost of n inserts. That's just the sum I equals 1 to n of ci, which is equal to, well, by this analysis, it's essentially n, okay, because that's what this thing adds up to, plus I just have to add the powers of 2 up to but not exceeding whatever my n was. So if I do my algebra properly there, that's up to the floor of log of n minus 1, okay, of 2 to the j. Okay, so I'm just adding up all the powers of 2 up to that aren't going to exceed my n. Okay, and this is what type of series? That's geometric, right? That's geometric, so it is bounded by its largest term, and its largest term is 2 to the ceiling. It's dominated by its largest term, 2 to the ceiling of log of n minus 1, which is at most n. Okay? And then all the other terms add up to at most n. So this is actually less than or equal to 3n, which is order n as we wanted to show. Okay? So that's algebra. Okay, so thus, the average cost per insert is theta of n over n, which is theta 1. So the average cost of an insert is order 1, which is what we would like it to be, especially if we're building a hash table. Okay? Even though sometimes we have to pay a big price, we've amortized that big expense over the previous insertions that we've done. So the overall cost of n operations is order n. And that's the notion of amortized analysis. Okay? That if I look at a sequence of operations, I can spread the cost out over a whole bunch of operations so that the average cost is order n. So if we sort of summarize that, okay. Okay, we basically, in an amortized analysis, we analyze a sequence of operations to show that the average cost per operation is small, even though one operation, or several even, may be expensive. Okay? There's no probability. Even though we're dealing with averages, there's no probability going on. Okay, when you do probability and you're looking at means, there's averages, right? Okay, here's another average, but there's no probability going on. Okay? It's average performance in the worst case. Because n operations take me a constant amount of time per operation in the worst case. N operations take me order n time. Okay, each operation takes order 1 time. Okay, but it's amortized over the n operations. Okay? Yeah, question?
Does one ever do amortized analysis on the expected case or whatever?
Yes.
Yeah.
Yes. Yes, you can mix,
But you don't have to.
but you don't have to. Yeah. Okay? But the point is that the basic amortized analysis is actually saying something very strong. It's giving you worst case bounds, but over a sequence, as opposed to looking at each individual element of the sequence. Now, there are 3 types of amortized arguments that appear in the literature. Maybe there are more. At one point, there were 2, and then a 3rd one was developed. So maybe there's a 4th. Okay? The first one is an aggregate, what's called an aggregate analysis. And this is what we just saw. Okay? Where basically you just analyze what do the n operations take. Okay. And then we're going to see 2 more today. One is called an accounting argument, and the other is a potential argument. These 2 are more precise because they allocate specific amortized costs to each operation. So one of the things about the aggregate analysis is that you can't really say what the amortized cost of a single operation is easily. Okay, you can in this case. You can say it's order 1. Okay, but in the accounting and potential arguments, it gives you a much more precise way of characterizing what the amortized cost of a particular operation is. So let's pitch in and look at the accounting method as our first method. So these we're going to go through exactly the same example. In some sense, this example, the easiest argument to make is the aggregate analysis. Okay? So we're going to get into arguments that in some sense seem more complicated, but turns out that these methods are more powerful in many circumstances. Okay? And so I want to do it in a simple situation where you have some sort of appreciation of the fact that you can look at any particular problem and approach it from different ways. Okay? Okay, so the accounting method is putting yourself in the position of a financial accountant. Okay? So what you do is we're going to charge the ith operation a fictitious amortized cost, we'll call it C hat sub I, where we're going to use the abstraction that $1 pays for 1 unit of work. In other words, of time manipulating the data structure or whatever. Okay, so the idea is you charge a cost. You say this operation will cost you, $5 or whatever. Okay? And that fee is consumed to perform the operation. But there may be some unused part. So if there's any unused amount, it's going to be stored in the bank. For use by later operations. So the idea is that if the fee that is being paid, the C sub I hat fee, isn't sufficient to pay for performing the operation, then you take money out of the bank to pay for it. Okay? And so you don't get arrested. What's the property that you got to have? You have to have the bank balance. What about the bank balance? What mathematical fact has to hold of the bank balance? Yeah, it better be greater than or equal to 0, right? Most people are familiar with that. That if it's so the bank balance must not go negative. In other words, the amortized costs minus the cost of the operations up to that point have to always be enough to pay for all the operations that you're doing. Otherwise, you're borrowing on the future. In amortized analysis, we don't borrow on the future. At least not in the simple ones we're doing here. Okay? So that means we must have that the sum I equals 1 to n of C sub I, the true costs, therefore, if the balance is not going to ever go negative, must be bounded above by the amortized costs for all n. Okay, for the bank balance not to go negative, if I add up the true costs, it's got to be the case that I can always pay for them. If I'm only charging, this is what I'm charging. This is what it actually costs me. So it better be the case that whatever I've actually had to pay to operate on that data structure, that's what this is, better be covered by the amount that I've been charging people for the use of that data structure up to that point. And that's got to be true for all n. But notice that this now gives me a way of charging a particular operation a certain amount. So the total amortized costs provide an upper bound on the total true costs. Okay? Total amortized costs are an upper bound on the true costs. Any question about this? Then we'll do the example of the dynamic table using this methodology. Okay. So, back to the dynamic table. Okay? So what we're going to do in this case is we're going to charge an amortized cost of $3 for the ith insert. Okay, for all I. And the idea is that $1 is going to pay for an immediate insert, and $2 is going to be stored for doubling the table when it needs to be expanded. Okay. When the table doubles, we'll use, of the stored dollars, we'll use $1 to move a recent item, I'll call it, and $1 will move an old item. So let's do the example. So imagine that I'm in this situation where I have a table of size 8, and I've just doubled my table. So I have 4 items in the table, and what I'm going to do is have stored no dollars in my table. Okay? So along comes an insertion of item number 5. Okay? I charge $3 for it. $1 lets me put the item in the table, and I have $2 left over. So let me store those $2 in the slot corresponding to where that item is. Now item 6 comes in. Once again, $1, charge $3, $1 is paid for the insert, I have $2 left over, let me play $2. Let me put it down there. And so forth. The next one comes in, $2, $2 left over, and now the 9th item comes in. So I double the size of my table. Okay? And now I copy all of these guys into all of these here. And what happens? Look at that. I've got $8 and I've got 8 items that have to be copied. Perfect. Okay? So one of these dollars pays for one of the ones that was inserted in the last round, and one of them pays for an old one. Okay? And so I copy them in, and now none of those guys have any money, and the 9th guy comes in, he has $2 left over. And then we keep going on, etc. Okay? So everybody, so you see that by that argument, I can say that if I charge everybody $3, okay, I can always handle all of the table doubling, the charges for the table doubling. Because the inductive invariant that I've maintained is that after it doubles, there's nothing in the bank account. And now I put in $2, well, then I can pay, and I'm now left in the same situation. Okay? And it's the case that the bank balance never goes negative. So that's really important invariant to verify. And so therefore, the sum of the true costs, or the amortized costs, upper bound the sum of the true costs. And since the sum of the amortized costs here is, if I go I equals 1 to n, okay, this is 3n. So the point is, this, I've now bounded the sum of the true costs by 3n. Okay? So let's go back to this table here and look to see what happens. Okay, if I put in C sub I hat and the bank balance. Okay? So in fact, so the first thing I do is insert, I charge $3, right? And I do an insert. How much do I have left? I'm going to have $2. Turns out I'm actually going to charge this $2 and have only $1 left. Okay? So this is, I'm actually going to undercharge the first guy. Okay, because if I charge, I'm going to show you that it works if I charge everybody $3 except the first guy I charge $2. Can actually save a little bit on number 1. Okay. Okay, then for this guy I'm going to charge $3. Okay, I've got to, what's the size of my bank balance when I'm done? Well, I have to copy one guy. He's all paid for, so I have $2 left. Okay? People with me? Okay, the next guy I charge $3. Actually, I'm going to charge all these guys $3. Okay? So here now, I basically get to, I've got a table of size 4, so I basically I have to copy, when I insert the third guy, I've got to copy 2 guys. That'll use up that, so I'll have only $2 left in the table after I've inserted him. Okay. Now I insert the fourth guy, okay, and that's a good one because now I've built up a balance here, $4, because I didn't have to copy anybody. Okay. Now I insert the fifth guy. I've got to copy 4 items, so that expends that balance. Okay, I charge 3. I have then 2 left. Okay, and then here, basically, I add 2 to it, add 2 to it, add 2 to it. Okay, and then at this point, I use it all up and go back to 2, 4, etc. Okay, so you see, one of the things I want you to notice is I could have charged 3 here, and then I would have had an extra $1 lying around throughout here. Wouldn't have mattered. Still would be upper bounded by 3n. Okay, so the idea is that different schemes for charging amortized costs can work. They don't all have to be the same. You know, it's not like when you do amortized analysis that there's one scheme that will work. I could have charged $4 to everybody, and it would have worked. But it turns out I couldn't have charged $2 for everybody. If I charged $2 for everybody, my balance would go negative. Okay? My balance would go negative. But I can charge $3, and that'll work. Okay? 4, 5, 6, I could charge that. The bound that I would get would be simply a looser bound. Instead of it being less than or equal to 3n, would be less than or equal to 4n or 5n or what have you. But if I tried to do 2n, it wouldn't have worked. Okay? Because I wouldn't have enough money left to copy everything. What would happen is I would have only $1 in this, and then when it came time to table double, I would need to copy 8 guys, and I'd only have built up a bank account of $4 if I only charged, if I charged $2 and had $1 left over. Okay? So to actually make these things work out, you have to play a little bit. Okay, see what works, see what doesn't work. Okay, no algorithmic formulas for algorithm design. Okay. Okay, good. In the book, you can read about table contraction. Okay, what happens when you start deleting elements? Now you want to make the table be smaller. Now you have to be very careful because unless you put, who remembers from physics hysteresis? Vaguely, a couple people? Okay, you have to worry about hysteresis. Okay, if you're not careful, if whenever it gets to be less than a power of 2, you go in half, you can find that you're thrashing. So you need to make it so that there's some memory in the system so that you only collapse after you've done sufficient number of deletions, okay, and so forth. And the book has an analysis of the more general case. Okay, so any questions about the accounting method? Accounting method is really very cute. Okay, very cute. And it's the one most students prefer to do. Okay, they usually hate the next one until they learn it. Once they learn it, they say, ooh, that's cool. Okay, but to start out with, it's a little bit more, takes a little bit more intestinal fortitude. Okay? But it's amazing. Good potential method arguments are really sweet. And we're going to see one next time. So you'll definitely want to review and make sure you understand it before Wednesday's lecture. Because Wednesday's lecture, we're going to assume we understand potential method. Okay. So let's do enough advertisement. I think the potential method is one of the beautiful results in algorithmic analysis. Okay, just beautiful result. Beautiful set of techniques. Okay, and it's also just in terms of, what do you aspire? To be a bookkeeper or to be a physicist? Okay, so the idea is we don't want to be bankers. We want to be physicists. And so this bank account, we're going to say that's the potential energy of the dynamic set that we're analyzing. Okay? So, because why? It delivers up work, just like a spring does, for example. Okay, when you study potential energy, or putting something up high and having gravity able to pull it down. We convert dynamic to potential, and that's exactly what we're going to be doing here, and it's similar mathematics, except that in our case it turns out to be discrete mathematics rather than continuous math for most of it. So here's the framework for the potential method. So we start with some data structure d0, and operation I transforms di minus 1 into di. So you view the operation on the data structure as a mapping one data structure to another data structure, the one from before to the one after. Okay, it's nicely mathematical. Okay, and of course the cost of operation I remains at CI. And now what we're going to do is define the potential function phi, which maps the set of data structures into the reals. So associated with every data structure now is a potential. Okay, a real valued potential, often integer potential, such that phi of d0 is equal to 0. So the initial potential is 0. And phi of di is greater than or equal to 0 for all I. So the potential can never be non-negative, just like the bank account, because the potential is essentially representing the bank account, if you will, in the accounting method. Okay, so we always want the potential to be non-negative. Now, actually, there are times where you use potential functions where you violate both of these properties. Okay, there's some really interesting potential arguments which don't violate these, but for the simple ones we're going to be doing in this class, we'll just assume that these tend to be true. Okay, but you may find we will actually see some times where phi of d0 isn't 0, but it doesn't matter. Okay, but generally this is what we're going to assume in the type of potential function argument that we're going to be doing. Okay, so I just want to let you know that there's a bigger space of potential function arguments than the one that I'm showing you here. Okay, so then under this circumstance, we define the amortized cost C sub I hat with respect to phi as, and this is one of these formulas that if you can't remember it, definitely put it down on your crib sheet for the final. Okay? So this is, so C sub I hat is equal to C sub I plus phi of D sub I minus phi of D sub I minus 1. Okay, so this is the change in potential. Okay, potential difference. And let's call it delta phi I for a shorthand. Okay? And let's see what happens, what it means to have in the different circumstances. So if delta of phi I is greater than 0, okay, so if this is greater than 0, then that means, what's the relationship between Ci hat and Ci? This is greater than 0. Yeah, Ci hat is then greater than Ci. Okay? Then Ci hat is greater than Ci. And what does that mean? That means when I do operation I charged more than it cost me to do the operation. So the extra amount that I charged, beyond what I actually used, is being put into the bank. Okay, is being stored as potential energy. So op I stores work in the data structure for later. Similarly, if delta phi I is less than 0, then Ci hat is less than Ci. And so the data structure delivers up work. Help pay for op I. Okay, for operation I. So if it's less than 0, that means that my change in potential, that means my bank account went down, okay, as a result. And so therefore, what happened was the data structure provided work to be done in order, because the true cost was bigger than the amortized cost. Okay? So sort of, if you think about it, the difference between looking at it from the potential function point of view versus the accounting point of view. In the accounting point of view, you sort of say, here's what my amortized cost will be. Now let me analyze my bank account, make sure it never went negative. In some sense, in the potential function argument, you're saying, here's what my bank account is all the time. Now let me analyze what the amortized costs are. Okay? So that's sort of the difference in approaches. One is you're sort of specifying the bank account. The other, you're specifying the amortized costs. Okay? So if we look at the why is it that this is a reasonable way to proceed? Well, let's look at the total amortized cost of n operations. Okay, that's just the sum I equals 1 to n of c sub I hat. That's the total amortized cost. And that's equal to, by substitution, just substitute ci hat for this formula. Okay? So that's ci plus phi of di minus phi of di minus 1. Okay? And that's equal to ci. And now what happens when I sum up these terms? What happens when I sum up these terms? What's the mathematical term we use for it? Telescopes. Okay? Every term on the left is added in once when it's I and subtracted out when it's I minus 1, except for the first and last terms. The term for n is only added in, and the term for 0 is only subtracted out. Okay, so this is because it telescopes. Okay, so this term is what? What property do we know of this? It's greater than or equal to 0. And this one equals 0. So therefore, this is greater than or equal to ci. And thus, the amortized costs are an upper bound on the true costs, which is what we want. Sum of the amortized costs is an upper bound on the sum of the true costs. Okay? But here, the way that we defined the amortized costs was by first defining the potential function. Okay? So the potential function it's sort of, as I say, the difference between the accounting and the potential method is, do you specify the bank account or do you specify the cost? Okay, do you specify the potential energy at any point or do you specify the cost at any point? Okay? But in any case, you get this bound. Also, this math is nicer math. I like telescopes. Okay? So the amortized costs upper bound the true costs. Okay, let's do table doubling. Over here. So to analyze this, we have to define our potential. Okay. If anybody can guess this off the top of their head, they're better than I am. Okay? I struggled with this for probably easily a couple hours to get it right. Okay, because I'm not too smart. Okay. That's the potential function I'm going to use. Okay, 2I minus 2 to the ceiling of log I. Okay? And we're going to assume that 2 to the ceiling of log of 0 is equal to 0, because that's what it is in the limit. So I take the limit for log of 0, this becomes minus infinity, so 2 to the minus infinity is 0. So that's just going to be a mathematical convenience to assume that. Okay? So where did I get this from? I played around. I looked at that sequence that I've erased, and I said, okay, because reversing, there are some problems for which defining a potential function is fairly easy, but defining the amortized cost is hard, okay, to define the accounting. So for this one, the accounting method is, I would say, an easier method to use. However, I'm going to show you that you still can do it with potential method if you come up with the right potential. Okay? So intuitively, this is basically what's left in the bank account at the ith operation, because I've put in 2i things into the bank, and I've subtracted out this many, essentially, from table doublings. Okay, up to that point. Okay? So first let's observe what is phi of d0. Zero. So that's good. And phi of di is greater than or equal to 0. Why is that? For all I. Why is that? So what's the biggest that ceiling of log I could be? Ceiling of log I is either log I or log I quantity plus 1. Okay? So the biggest it is log I plus 1. If it's log I plus 1, 2 to the log I plus 1 is just 2i. That's the biggest it could be. Right? So 2 to the log of I plus 1 is just 2 times, this is just, let's do it the other way, is I times 2. Okay, I for that part, 2 for that part. Okay, so that's the biggest it could be. Okay, or it's just log of I. So either this is going to be 2i minus I or 2i minus 2i. In either case, it's bigger than 0. Okay? So those are the two properties I need for this to be a well-defined potential function. Now, that doesn't say that the amortized costs are going to be, satisfy the property that things are going to be cheap, okay, that I'm going to be able to do my analysis and get the kind of bounds I want. But it sets it up to say, yes, I've satisfied the syntax of having a proper potential function. So let's just do a quick example here, just to see what this means. So imagine that I'm in the situation where I have 8. Did I do that right? Yeah. Okay, 8 slots, and say 6 of them are full. Okay? So then phi by this is going to be 2i. That's 2 times 6 minus 2 to the 2i. What's that? Sorry, minus 2 to the ceiling of log I. So I is 6, right? So log of I is, log of 6, the ceiling of it is 3. So that's minus 2 to the 8th. Minus 2 to the cubed, which is 8. So that's 12 minus 8, that's 4. Okay? And if you think about this in the accounting method, these would be zeros And these would be 2's, right? For the accounting method. If we did the same thing, because this is halfway through, right? All zeros, and then we add 2 for each one that we're going in. So my function is, in fact, telling me what the actual cost is. Okay? Everybody with me? Okay, so that's what we mean by this particular potential function. Okay, so now let's add up the amortized cost of the ith insert. Okay, so that's the cost of the amortized cost of the ith insert, just by definition. Okay. And now that's equal to, well, what is C sub I? Do we still have that written down somewhere, or have we erased that at this point? Sub. I think we erased it. Okay. But we can write it down again. It is I if I minus 1 is an exact power of 2. And it's 1 otherwise. That's the C sub I. That's this term. Plus, and now phi of di. So what is that? Phi of di is this business. 2I minus 2 ceiling of log I minus 2I minus 1 minus 2 ceiling of log of I minus 1. Okay? So that's the amortized cost. That's pretty nice, pretty formula, right? Okay, let's hope it simplifies a little. Okay. So that's equal to, well, we have the I and the 1 here, if, etc. That business, plus, okay, well, we have some things we can cancel here, right? So in particular, this stuff we can cancel, right? So here we have 2I minus 2I. That cancels. And then we have what's left over here is a minus 2, so that's a plus 2. And now I have minus this term plus this term. Oh, that's a lot prettier. Okay, still a mess. Got to do a case analysis. Why is it suggestive of a case analysis? We have a case. Okay, so let's do a case analysis. Okay, so case 1, I minus 1 is an exact power of 2. So then Ci hat is equal to, well, Ci is now just I. That's that case. And then we have the rest there, plus 2 minus 2 ceiling of log I minus 2 ceiling of log of I minus 1. Okay. And that's equal to I plus 2. Well, let's see. If I minus 1 is an exact power of 2, what is this term? I minus 1 is an exact power of 2. Plus. Thank you. Sorry about that. It's good I have students, let me say, because, boy, my math is so bad. This is actually why I end up being a pretty good theoretician, is because I don't ever trust what I've written down. And so I write it down in a way that I can verify it, because otherwise I just am not smart enough to carry through 5 equations in a row and expect that every one is going to be transformed appropriately. Okay, so you write it down, so I always write it down so I can verify it. And that, fortunately, has the side benefit that other people can understand what I've done as well. Okay, so what is this one? This is 2 to the log of I minus 1, because the ceiling, if this is an exact power of 2, right? Then ceiling of log of I minus 1 is just log of I minus 1. So this is 2 to the log of I minus 1, which is I minus 1. Right? Yeah? Okay. Okay, if it's an exact power of 2, then the log is an integer. Right? So taking the ceiling doesn't matter. Get rid of the ceiling. Okay, this one, however, is not an exact power of 2. But what is it? It's just one more than this guy. We know that I minus 1 is not an exact power of 2, so it's going to be the next bigger one. Okay? So that means this is what? So it's going to be, how do these two compare? How much bigger is this one than this one? It's twice the size. We know what this one is. Okay, or we can reason it from first principles. This is going to be the log of I minus 1 plus 1. Okay? And so then you can reduce it to this. Okay? So you've got to think about those floors and ceilings, right? It's like what's happening in the round off there. Okay? So now we can simplify this. Okay, so what do we have here? We have, okay, so I have, if I multiply this through, I have an I plus 2 minus 2I plus 2 plus I minus 1. Okay? A lot of people, I know a lot of you, probably 90% of you won't do this step. You go directly from this step to the last step. And that's where 30% of you, or some number, will get it wrong. Okay? So let me encourage you to do that step. Okay? It's easier to find your bugs. Okay? If you take it slow. Okay, actually taking it slow is faster in the long run. Hard to teach, young stallions or fillies or whatever, okay? Hard to teach to just take it easy, just patience, just do it slow, get it right. It's actually faster. Okay, everybody knows the tortoise and the hare story. Yeah, okay? But nobody believes it. Okay. Okay, so now here we have, let's see, we have 2I here, an I here, and an I here. And then that leaves us with 2 plus 2 minus 1 equals 3. Awesome. Awesome. Okay, amortized cost is 3 when I minus 1 is an exact power of 2. Okay? Case 2. Okay, I minus 1 is not an exact power of 2. So then we have C sub I hat is equal to, now instead of I, it's 1 plus, and then the 2 minus 2 to the ceiling of log I plus 2 the ceiling of log of I minus 1. Okay, now what can somebody tell me about these two terms in the case where I minus 1 is not an exact power of 2? What are they? Equal. Why is that? Yeah, the ceiling is going to do the same thing to both. It's going to take it up to the same integer. So these two things are equal. Which means this is equal to 3. Okay. So therefore, n inserts. Okay. So now I say, oh, the amortized cost is 3 for every operation, for every insert. So therefore, n inserts cost, well, the amortized cost of each is 3. So n of them, the amortized cost is 3n. That's an upper bound on the worst case true costs. So n inserts cost order n in the worst case. Okay, there's a bug in this analysis. It's a minor bug. It's the one I pointed out before. The first insert has an amortized cost of 2 and not 3. I didn't actually deal with that one carefully enough. Okay, so that's an exercise to just go and look to see where it is that that happens and how you show that in fact the amortized cost of the first one is 2. Okay, where that shows up. Okay, so to summarize, actually let me summarize over here. Conclusions about amortized analysis. So amortized costs provide a clean abstraction for data structure performance. So for what I can tell somebody, so suppose I've built a dynamic table, for example. Okay? It's easier to say, in terms of your own performance modeling, it costs a constant amount of time for each insert. As long as you don't care about real-time behavior, but only the aggregate behavior, that's a great abstraction for the performance. Rather than saying, it's got that complicated thing which sometimes costs you a lot. How do they reason about that? Okay? But if you can say every operation costs me order 1, that's really simple. Okay? But they have to understand it's order 1 in an amortized sense. Okay? So if they do have a real-time constraint to meet, amortized doesn't cut it. Okay? But for many problems, it's perfectly good. Okay, lets me explain it rather simply. Okay, we will see some other data structures that have amortized costs where different operations have different amortized costs. And the nice thing about that is I just add up what's the cost of all my different operations, okay, where there's a different cost for each operation. Some will be log n, some will be order 1 or whatever. Add them up. That's an upper bound on the true costs. Okay? Tremendous simplification in abstracting and reasoning about those complicated data structures. Okay? Now, so this is probably, this is huge. Okay, abstraction, you know, computer science, what we teach you through 4 years of undergraduate and another year if you go on to MEng, and if you get a PhD, it's another 15 years or whatever it takes to get a PhD. Okay? All you teach about is abstraction. Abstraction, abstraction, abstraction. Okay? So this is a powerful abstraction. Quite good. Now, we learned 3 methods. In general, any method can be used. You can convert one to the other. But each has situations where it is arguably simplest or most precise. So any of the methods can be used. However, you must learn all of them, okay? Because there are going to be some situations where you need one, where it's better to do one, better to do another. Or if you're reading in the literature, you want to know these different ways of doing it. And that means that even though you may get real comfortable with accounting, okay, on an exam or whatever, I may say, solve this with a potential function argument. Okay? So you want to be comfortable with all the methods. Okay? Last point is that, in fact, different potential functions or accounting costs may yield different bounds. Okay? So there's nothing, when you do an amortized analysis, there's nothing to say that one set of costs is better than another. So just as an example, okay, in any data structure generally that supports delete, I can amortize all the deletes against the inserts. So in general, what I could do is say, deletes are free, okay, and charge twice as much for each insert. Okay, charge enough when I do the insert to amortize it against the delete. That you could do with an accounting method. You could also do it with a potential method. The potential then being the number of items that I actually have in my data structure times the cost of a delete for each of those items. Okay? So the point is that I can allocate costs in different ways, or I could have amortized costs which are equal to the true costs. So there are different ways that I could assign amortized costs. There's no one way, okay, and choosing different ones may yield different bounds. May not, but it may yield different bounds. Okay? Generally, it does yield different bounds. Okay, next time, an amazing use of potential functions. Okay, this stuff is cool, but let me tell you, Wednesday's lecture, amazing, okay? Amazing the type of analysis we're going to be able to do.